Okay, I think we are nearly complete. So let's try to start. All right. First, hello everybody, and thanks for joining my talk. I expected a not so crowded room, so thank you very much for coming here. And I think it's amazing to see so many people, especially in our front-end conference, to joining the topic of front-end developing, and that's something which is connecting us, and this always lets me feel like family, and maybe it's the same feeling for you. So I hope my excitement goes down now, because I am beneath under my family. So yeah, before we start, I would like to introduce myself. So my name is Georgios Kaleadis, and I learned programming with Flash 4 in 1998. And maybe there are some Flasher out there. Yes, 2 hands, 3, 4, perfect. Because I asked this question before, and it was like a single hand. And yeah, I think the Flashers are going less and less, but nice to have you here. Today, I'm a front-end developer using Angular in my daily job at Satellites in Munich, and React or Vue for my pet projects. In my spare time, I teach coding to kids, and I love experimenting with technologies like WebGL, my Arduino, algorithms, and also a little bit of virtual origami. My talk today has the title Stargazing for Developers, and we are going to build a beautiful twinkling night sky with basic web technology. So let's start. Over the course of 4 chapters, I will take you on a journey to the stars. We will explore how a single star is working to create them easily. After that, we will assemble a full and crowded night sky. Shooting stars can't miss in any night sky, and that's what we'll look at in the 3rd chapter. And the final chapter will show you what constellations are and how we can build them. During our chapter, we will discover new science facts, and I marked them with these emoji stars, followed by an idea how we can creatively code that fact. Speaking of coding, you will see today's SVG markup together with CSS animations and CSS variables to create the actual animations. And at some point, we don't want to repeat ourselves. We will use plain JavaScript to create many variations of our SVG code and to modify the CSS variables. Let's start with the 1st chapter. We want to know how our star is working so we can build one ourselves. We want to observe a single star. I picked a little dot that we can see with our naked eye. The star is called Betelgeuse, and you can see it in the famous Orion constellation. Betelgeuse is more than 600 light years away. We would travel for 600 years with light speed, but with my developer superpower, I can fast forward to save us some time today. So we arrived at Betelgeuse. Let's ask our first question. What is a star? The scientific answer is a bright ball of gas with a nuclear fusion producing a lot of heat. If you cut open a star, you can see it burning in the center. And usually everything would fall apart because of all the heat it's producing. It's the gravity that keeps everything in balance and shapes it like a ball. And did you notice? We earned our first star fact, hot gas ball. And the idea is to create an SVG circle that represents that gas ball. And how do we implement it? We use an SVG circle. The circle is given a radius r and a color with the fill attribute. And once created, it will look like a star. Well, a very rough one, and the color hot pink seems a little bit off in this example, but this brings us directly to our next question. What's the color of a star? The sun has a surface temperature of around 5,500 degrees Celsius. Betelgeuse is much colder, with a temperature of 3,200 degrees Celsius. Both stars are still very hot, and they look reddish. So you could now think red means hot, but it's quite the opposite. Look at this blue star. It's called Eta Carina, and its surface temperature is more than 30,000 degrees Celsius. So in reality, the really, really, really hot stars are blue and not red. So we have a new star fact. Temperature is color. And the idea is to create some circles with different colors. So we create 3 circles, each with a different color from hot to cold. That's not too bad, but all circles have now the same size. Let's continue to our next question. How large is a star? We all know that the sun is huge. It's 1 million kilometers in diameter. But now watch this comparison video. We start with the Earth, followed by the sun. That's nothing new, but now Eta Carina comes into the game, and that's gigantic. But Eta Carina is nothing compared to Betelgeuse coming now into the display. But Betelgeuse is still smaller than VY Canis Majoris, one of the biggest stars ever discovered in the visible universe. Just look how small the sun is. You can see it here, it's merely a pixel, and you can see the blue dashed line here. You can see it here in a larger image. That's the Earth orbit around the sun. So VY Canis Majoris is really gigantic. And the next star fact, stars have different sizes. So let's plug in some different radii and look at the result. So we have our known group of circles again, now with different radius values applied. The result looks like this. I mean, that's okay, but we will never create a night sky if we have to create all the circles manually. We want to create this markup with JavaScript. I also added a transform so we can easily change the position. And I want to use a function called createStar, where I can just pass in all the information I need to create that star. And the function itself looks like this. There's a custom create SVG element function I wrote to save me from the struggle with the document.create element namespace and so on, because that's required if you want to create SVG elements. Then you can see some append child. That's basically the same you use with HTML. It works with SVG elements too. And in the end, there are some properties we want to set because we need the radius, the filling, and the position. Nothing more is happening in our createStar function. And with that function, we can now create vast amounts of different stars. So we're ready to build our night sky. But to observe our night sky, we need to travel back to the Earth first. And arriving at the Earth, we can see the beautiful night sky, and one question of a romantic stargazer is inevitable. How many stars are in the universe? So a romantic would say, more stars than the Earth has sand grains. And scientists would maybe say 1 quadrillion stars. But all those numbers, they're not really helping here. So maybe we should rephrase our question to how many stars can we see in the night sky? The answer is exactly 9,096 stars in a pitch black night. And actually, it's only half of it as we are living on a globe and we can only see half of the sky at any given position. And it gets so much worse with light pollution. Look at that image. More and more stars are disappearing from the right to the left. You can see how your location on the Earth affects the total count of stars. Standing at a city center here in Bucharest, you won't be able to see more than 35 stars in the whole night sky. Compare this with the high numbers that you get when you go to the deep rural areas far, far outside of the city. So, the next star fact, star count. And the idea is to create a lot of stars. So we want to use a JavaScript function where we can pass in the total count of stars we want to create. And the function itself is a for loop which will create the stars with a random color, a random position, and a fixed size of 1. The result looks like this. And that was surprisingly quick with the power of JavaScript. So just imagine that you would have to create this manually in Sketch or Figma. But it looks boring. So let's try to add an effect. The subtle effect you can see here is called twinkling. Or, as we all scientists today, it's also called astronomical scintillation. And the effect is caused by our atmosphere when the light travels through different layers of air with different temperature. And it's more or less the same effect you can see in a swimming pool where the light travels to the ground. That's a star zoomed in from the Earth through the atmosphere. And you can clearly see that there are changes in brightness and position, even color and shape. And that leads us to our newest fact. Stars can twinkle. And we are going to implement it with 2 CSS animations to change the scaling and the opacity of the stars. So the first CSS animation looks like this. We use a keyframe animation here at the top and apply a rather random looking scaling. So you can see it here, some random scalings. And the rather rough animation is intended as we want to create the illusion of randomness as you're surprised by the different changes in the scaling. The animation itself is running forever and it's alternating, so it's going back and forth, which increases the animation cycle and makes it a little bit more natural. The next CSS animation is more simple. Our star should fade in and should fade out. And we use again a keyframe animation where we go from 100% to 10% opacity. Nothing more here. And when we combine both animations, it will animate the scale and the fade in parallel. We use different timings here. So you see 5 seconds and 2 seconds, because this again creates a more natural animation because they're not always starting at the same position. So the animation cycle is again more bigger than if they compared to being starting at the same time. All right, let's create 3 circles and apply our animation. The result looks like this. And this looks really artificial because everything is in sync. You can clearly see how the result looks more natural when it's asynchronous. We use the power of CSS variables to fill the CSS property animation delay here. With that property, we can delay a CSS animation, and we will receive a value of 0 here, so no delay, if that CSS variable is not given. But we can apply different values to our individual stars through CSS. The applied animation offsets here, maybe you have seen it, are negative because maybe some of you know it, maybe some of you not. I didn't know that before researching for that presentation, is that the animation value, when it's negative, it starts in the mid of the animation and starts immediately. And maybe some of you witnessed that if you introduce an animation delay, that stupid animation is not going to start until the first delay is going past. So by using negative delays, we can start in the mid-action, get the offset of the animations, but no waiting in the beginning. So we can now add the twinkling effect animation to all of our stars in the sky, just by modifying the create star function we created earlier. So first, we add the CSS class twinkle little star we just created to provide that the combination of the animations. And next, we assign a random and negative delay to our CSS variable to offset the animations. And the result looks already awesome. And I kept a large circle here in the foreground so you can see how an animation looks differently when it's being applied to a small object, because, I mean, who would have thought that the large star here in the foreground could look beautiful like the masses of stars in the background? Here's another version with the sky only. And that's pretty nice, and we have come really far in a short time already. So let's jump to our third chapter. The twinkling sky we've just built is beautiful already, but it's missing a little bit of action. That's why I want to see some shooting stars appearing. Let's explore what shooting stars are and then create some. So, what are shooting stars? They are pebble-sized rocks that enter our atmosphere. That thin blue line you can see here, and the rocks, they travel with a speed up to 260,000 kilometers per hour. The speed, in combination with the friction of our atmosphere, makes it burn and light up. We are lucky most of them are so small that they burn up entirely before reaching the Earth. Next star fact. Shooting stars are flying burning rocks. And the idea is to create a moving circle with a little bit of fading. So, we use a circle again. But this time it stands for a little piece of rock. It's not a gigantic star. And to simulate the burning, we use opacity. So we are not visible in the beginning, then we are going to burn fully, and then the burning stops slowly, so we are going back to opacity of 0. And the result looks good. So let's build some movement. So we want to move the circle in something like an arc. And we start by rotating it from 0 to 180 degrees. But something is wrong with the result. You can't really see it rotate. If we look at a larger version and attach some little shape onto that disk, we can see that it's indeed rotating, but around itself only. We need to offset the center of the animation. So, in addition to the rotation, we also translate now. So that part with rotate was before, and now I added a translate to the whole transformation group. And the translation has the effect that the circle is rotating around its original position, marked with the red dot here, and it's using the radius of 100 pixels that you can see here in the translate. But order matters. So don't translate and then rotate. Otherwise, you would shift the circle by 100 pixels on the x-axis and then rotate around yourself again. So maybe some of you didn't know that, but that order here in the transform thing matters. So this is the correct. The start angle, that value here, is going to change, and also the end angle, and the CSS animation is instantly adjusting to reflect those values. So, we have a shooting star where we can provide variations with CSS variables. So let's build a function called createShootingStar, where we can pass over all the required values. The method itself will only build the SVG structure and apply the CSS variables and the attributes. Nothing more is happening again in this function create shooting star. And the result looks like this. And when we disable all the visual helpers, because maybe some of you wondered what are those yellow shapes and the red paths, that's just helping me to reflect the values and to make sure that everything works, because a shooting star is not visible all the time, so it would be really hard to develop it. And now I disabled all the helpers and we have a shooting star. But there's a question missing again. How many shooting stars are actually happening in the sky? During a usual night and outside of a city, you can observe up to 6 shooting stars. But during a meteor shower, you can observe up to 200 shooting stars per hour. So it's worth to wait for a meteor shower and maybe try to sit outside and look into the sky. We have a new star fact, meteor shower. And the idea is to create multiple random shooting stars. So we use our create shooting star function we created to create 3 different configurations. And the result are multiple shooting stars again. But they all start at the same time and they're shooting forever and ever. To change this, we hide the shooting star in the beginning and only show it and apply the animation when the class is-shooting is present on the star. We use a function shootNext to randomly assign that class here to a random shooting star we select from our group of shooting stars being present. And we also remove it from the shooting star before if there was any. And the result looks like this, where each shooting star is randomly activated now, and so you won't see any shooting star shooting while the other one is shooting. So let's try to combine our sky with the shooting stars. And there we go. I mean, this looks really nice already. And you can see the stars twinkle in the background and the shooting stars appearing randomly. So our final chapter is about constellations. And we start with a little bit of science again. So here you can see a picture of random everyday objects. Although we all know that those pictures show no living things at all, our brain still recognizes them as characters and faces, and even together with an emotion. My favorite is the grumpy broom and the happy brush family here. And this behavior also has a name. It's called pareidolia, and it's the human tendency to see patterns of faces in random data. So that should be your next part effect to explain to the people. And what are stars in the sky? They are random data, so that our brain tries very, very hard to find anything meaningful in it. I get some distance. So just look at this random star pattern. You can make some connections between the stars, which will create a line drawing that can be further imagined as a full image. And centuries ago, and thanks to pareidolia, this patch of stars transformed into Orion, a famous hunter from the Greek mythology. To spot him, look out for Orion's belt. Those 3 stars here, those are the brightest stars in that constellation and makes it easy to spot him if it's January to March in Europe. So you have to wait until next winter, maybe. And besides Orion, there are 2 other must-known constellations in the sky you should really, really know. That's Ursa Major, which is Latin and translates to big bear. And many people will recognize the upper left part here as the Big Dipper in English, or in Romanian, Carul Mare. Thanks. And Big Dipper, so that part here, is not a constellation by itself. It's just like the 3 stars in Orion's belt, and they help you to find the big bear here, and it's not a constellation by itself. So that's maybe another part effect you could remember if someone wants to convince you that this is a constellation. And here's the third one. That's Hercules, son of Zeus. He's a great hero in the Greek mythology. And in the northern hemisphere, you can spot him from spring to fall. And to spot him, just look out for his torso. Those are the 4 brightest stars again in the constellation. There are many, many more things people see in the sky. Today, there are exactly 88 constellations in the sky, and they are distributed around a virtual globe around the Earth. There's nothing more to find than those 88 constellations. Constellations are imaginary images, and that's our new star fact. And the idea is we will build them by connecting SVG circles with lines. So this will be our basic building block here. 2 dots connected with a line. And if we can create such an element, we can virtually create any thinkable outline there. And to make our lives easier, let's think about creating it with JavaScript in the beginning, from the beginning. So first, we need to collect our 2 endpoints as a list of coordinates. We can pass that list to a function called createDots to create the 2 dots here. Next, we call a function createLine where we can build the path element. And maybe you have spotted that part here. That's the interesting part in the createLine function, because we receive a list of points, and with a custom function, generateLinePath, that's something I wrote to create that magic string here. And that, if it's magic to you, basically means move to 0, 0 in this example, align to 100 and 0, and so on. So this function will take whatever points you give and transform it into that magic string, so we can assign it to our path data attribute. Let's try to build more complex shapes. We start with 4 points and create the 4 dots as usually with the createDots function. But how would we create this hot pink line here? We can't just pass in all the points we have to our createLine function, because the createLine function is simple, it should be simple, and it will just connect all the dots it's receiving in the order they are received. So it's going from 0 to 1 to 2 and 3, the order they are appearing here. Instead, we define the line as a list of numbers we want to connect. And those list is just referring to the dots we want to connect. So in this case, it's 0, 3, 1, 2. And how are we going to implement it? We use a function indices to points, which is just transforming that number back to the actual point. So we are just in time collecting the points in the order they should appear, and then we continue with our createLine function as we did before. To create a constellation like this one you can see here on the right, we want to call a function createConstellation and pass in the star coordinates, so we can create all the dots here, and a list of lines to connect the dots here. It's then only a matter of the data we pass in to create our hero, Orion, here. Inside the function, there is the createDots function we created and the createLine function together with the indices to points. This time it's working with an array of the lines we want to connect, but nothing more has changed. So that should be pretty comprehensible. And by switching the createDots function with our createStars function, we can get back to our twinkling stars, so it fits a little bit better in our twinkling night sky. So when Orion is placed in the night sky, it looks already very good, but something is missing. With a single bonus fact left: appearing constellations. because constellations are hard to find and even harder to imagine. And that's exactly what we want to animate or to creatively code. They should appear slowly over time in the sky. So the idea is to create animated SVG paths so that the constellation can appear over time. We will use a technique pioneered by Jake Archibald in 2013. It's a smart combination of dashes and dash offsets on a path to create illusion of a revealing path. But first, a quick summary what dashes and dash offsets do in a path. Dashes are created through the property stroke minus dash array. And you have here a 100 pixel line so you can see how the different configuration affects it. And what is it doing? It's not telling you how many segments you want, because you could think here, well, I have here a 10, so maybe it's just 10 segments. That's just a coincidence, because if you have a number that is not fitting into the 100 pixel, something is fishy. So what it's doing, it's creating a segment with the length of 30 pixel here, a gap of the same length, and so on until the line ends. And so you get a dashed path in SVG. And here's a little demo to visualize the dash offset. So we have the stroke dash array to configure the segments. Now we have the dash offset, so we can shift it a little bit. And I wanted to make an interactive demo because sometimes it can be a little bit abstract to think about it. So what you see here is our original line with our stroke dash array set to 10 pixels. So we have segments of 10 pixel, gap, segment, gap, and so on. If you imagine that line longer, infinite longer, it would look like so 10 pixel, 10 gap, 10 pixel segment, and so on. In addition to that infinite line, I let a yellow window floating over it. And the yellow window is getting pushed by the dash offset. So it's currently set to 0. Now I'm going to change that offset with JavaScript in small steps. And you see that the window gets pushed further and further the higher the dash offset is here. And if you remove the infinite line around it, you can see how the content would look like if this is maybe a looking window onto your infinite line. And if you pretend just for a second that that window is not moving, but still showing the changes, you get the final result, and that's how your original line would look like with the current dash offset applied. And now comes the Jake Archibald magic. Our offset is set to 100 here. So the dash array configuration is still the same, 10 pixel, segment, and so on. And the dash offset is 100. 100 matches exactly the length of the original line, which means that the looking window is pushed exactly at the end of our original line. So you can see here, those endpoints are matching. I will now switch the dash array to a new value. So it switched from 10 to 100. So our new configuration is now, you can see it on the infinite line, a segment of 100 pixel, a gap of 100 pixel, a segment of 100 pixel, and so on. So what happens if we now go from the dash offset 100 down to 0? You can see that it's going over that line, and here you see the final result, which is a revealing line, exactly what we wanted to achieve. You can create a CSS animation from that knowledge, and with that CSS animation, we can reveal any given path out there. So we assign the length of our path. So it was 100 pixel before, but now I want to use a CSS variable. And yeah, we assign it to the dash array. So this creates the correct segment and gap configuration. And next, our animation should start with the dash offset of the same length. So this is pushing the window at the end. And when we let the animation run, we want to pull that window back to the original position, which creates our revealing animation of the line. And to use that animation, we can create a CSS class, assign the required configuration. In the example before, it would be 100, and apply the animation, so the variable picks up the different values. The result looks like here. The red line is 100 pixel. We used the animation structure we just explained. I have here the debugging helper, so you see how the sliding over the segment is revealing the path at the top. You're in big trouble if you use a wrong path length, like here, because the hopping path here is clearly longer than the 100 pixel of the red line here. And the hopping path is a diagonal line, so we have already problems seeing the full length of it. Maybe we should calculate it or whatever comes to help you in that situation. What I want to illustrate is that a path can be diagonal, it could be a handwriting, it could be some weird shapes. There are so many path structures, path variations out there, you can't spot the length to put it into the CSS variable. With JavaScript, you can use the method getTotalLength on the path element to retrieve the length of any given path out there. And that length can be assigned to the CSS variable path length again, and our configuration is fixed and the hot pink line is revealing. So let's animate all the lines. And this looks bad because they all start at the same time. So let's assign delays as we did with the shooting stars before. This time we assign positive values because we want to wait for the animation to start. So a negative value would be wrong here. And here you can see that that animation here is waiting for the others to complete. And that's not some callback magic, it's just a smart combination of delays here, because the animation duration is 1 second of each line revealing. So we have 1 second here, 2 here, 3 here. So we can just delay by being smart. We can delay them correctly so they look like they're building. And it's surprisingly easy to apply our knowledge to the existing constellations. Provide a CSS class where we can assign the animation delay with a CSS variable and use the reveal path animation we created before. Then, inside our existing createLine function we created earlier, we want to assign that CSS class together with the path length. We read it with the path getTotalLength. And for the delay, we have to be, again, a little bit smart to ensure that all the different paths are building up correctly. And when this is done, you can see that our constellation is building up correctly. We can use our function to create easily multiple constellations in the sky. Here are the top 3 constellations I told you about before. Let's wrap up what we have learned. So we explored Betelgeuse, a star far away, to discover how stars can be built. Back on Earth, we looked in the sky and learned how we can build a twinkling effect from 2 simple animations, the scaling and opacity. And we discovered how variations of shooting stars can be created with the power of CSS variables. And in the last chapter, we explored path animation techniques to create a revealing constellation. Thank you for listening. I hope you enjoyed the evening. And this animation is being done with exactly the CSS animation I did before. I just scribbled it with my Wacom. And you can find here the URL to the presentation, my social handles, and a little bit from my company. Thank you very much. So, any questions? Sorry? What I did or where I did this from, or what is my daily job?
What's your job?
I'm a front-end developer. I mean, I'm doing awesome front-end stuff, and
Stargazing front-end developing, right?
yeah, it is somehow, isn't it? And someone asked me how I created all the constellations, because how did I get to all the coordinates? And it's simple as dropping in an image from a constellation in Figma is my tool of the at the moment I'm using. Just drop it in, put some dots over there, read the coordinates, then I have the coordinates, and then just manually connect it with 0 and 1, and so I created all the arrays, and that's how I created my constellations. Yes?
Is there a limit to the number of stars we can render?
Yes, surprisingly, it's a really good question, because maybe you've noticed that I didn't create the full set of 4,500 or even 9,000 stars, because I imagine that I'm using CSS variables, I'm using animations, so the browser shouldn't have any problems rendering it. But surprisingly, it's going really quickly down because there are a lot of things to calculate, and that's already too much for a browser. So you can create millions of stars with CSS animations. WebGL would be possible to use the same techniques there and create maybe the stars there, for example. Okay, if there are no questions left, let's go to the coffee, or is the keynote now happening? I don't know. Coffee, good. Thank you very much.